Hello everyone, welcome to my talk on kinetic field theory. My name is Carsten Littek. I'm a postdoc at the Institute for Theoretical Physics in Heidelberg, and I'm going to focus on velocity statistics of large-scale structure in the universe. I assume you've seen the introduction video by Ellen Kozlikin on kinetic field theory, so I will only give you some basic ideas of KFT here. The velocity field is interesting because it's hard to calculate its statistics from hydrodynamic approaches. First of all, it's going to stay irrotational for dark matter because the Euler equation does not contain any sources for vorticity, and also the hydrodynamic approach is going to break down as soon as dark matter streams cross. So that's where kinetic field theory comes in, as it is a particle-based approach. We're looking at an ensemble of n particles that are moving through phase space according to the Hamiltonian equations of motion. So their trajectories are never going to cross. We can write down the particle motion by means of a retarded Green's function, and we're going to split the motion into an inertial term and some interactions right here. Writing it in this way allows us to include interactions either perturbatively with a Taylor expansion or calculate a mean field interaction term that weights the interaction between particles with their correlation function. The main quantity of this theory is the generating functional, which depends on the source field J, which allows extracting information about the positions of particles and the density, for example. For the velocity field, we have to realize that our basic fields in this theory are the positions and the momenta of each and every particle. So the particle velocities or momenta do not contain any spatial information. So in order for a particle to contribute to the velocity field at some position, we need to impose that it can only contribute at its respective position, meaning that we have to multiply the momentum of particle I with a Dirac delta distribution that chooses the position of the particle. By that, we transform our velocity field into a momentum or a velocity density field, because this Dirac delta here is exactly the one particle density in real space. Going into Fourier space, we pick up this Fourier factor right here, and in order to express this as an operator, we replace each position and each momentum of a particle with functional derivatives with respect to the source field J, with either the momentum or the position. In order to calculate the two-point correlation matrix, we simply apply two of these operators to the generating functional and set the source field to 0. In order to get scalar power spectra, we can project the momentum density field on the wave vector. Thereby we obtain the divergence field of pi, or to the transverse, project this on the transverse direction of k, thereby obtaining the curl of the momentum density field. We did this, and that's what's shown right here. In blue, it is the divergence. In red, you see the curl of the momentum density field. And the dashed lines represent the power spectrum due to the inertial motion of particles, while the solid lines include interactions between particles up to linear order in our perturbative approach. So what I want you to notice is that on all scales, we gain power due to the interaction. And especially on the nonlinear scales, we gain, compared to the inertial motion, a lot of power, a lot of nonlinear evolution right here. Now, what can we use this momentum density field for? For example, for the Z effect, which is anisotropies in the cosmic microwave background due to inverse Compton scattering of the CMB photons with free electrons in the intergalactic medium. I'm going to focus here on the kinetic SZ effect, where these electrons are moving with the bulk of structures relative to the Hubble flow. So the temperature distortion, delta T over T, is given by the Thomson cross-section and an integral over the line of sight, weighted by the optical depth, and the projection of the momentum density on the line of sight direction. Of course, at this point, we are kind of ignoring things like the ionization fraction and the fraction of baryons compared to dark matter. But we want to focus here on the statistics of dark matter as well. So the angular power spectrum is then given by a Limper type equation with an integral over the line of sight and the three-dimensional power spectrum of the transverse component of the momentum density. The parallel component vanishes actually when we integrate over the line of sight. And what we're going to do is compare KFT results with linear and nonlinear results in the hydrodynamic approach. So linear theory, the classical result was obtained by Vishniac in 1987, and he realized that the linear power spectrum of the transverse component has to come from cross correlations between the density fluctuations and the velocity. So assuming that these two fields evolve linearly, he obtained this upper result right here. And what we did in kinetic field theory is we assumed inertial motion and expanded our initial correlations up to quadratic order in initial momentum correlations. Thereby we obtain also a mode coupling integral of two power spectra with a slightly different kernel than Vishniac did. We are missing the factor of 2 right here. So looking at the plot, we see that for the very smallest scales right here, we obtain the same result, but for the linear scales or the larger scales, our result is off by a factor of 2. Otherwise, the dependence on the scale factor, on the wave vector right here, is the same. It is k square as we expect from momentum conservation. Going to nonlinear theory, we compare with Park et al. 2016, who schematically did the following. They used Wick's theorem to write the power spectrum into terms that are products of 2-point correlations and another term that is the connected 4-point correlation. For the connected term, they used one-loop order calculations, which are quite hard to do. For kinetic field theory, we used mean field interactions, which made the calculations a lot easier, as we only have to solve an integral over derivatives of the first the correlation function. Comparing the results directly, we see this. So first of all, for the largest scales, we obtain almost the same results. Going to smaller and smaller k, so calculating the limit k to 0, we obtain the same dependence on the wave number k, that is k squared, as we expect from momentum conservation. But then our mean field theory result here leads to more power on almost all scales, and especially the nonlinear scales, which probably comes from the fact that the mean field contains more nonlinear dynamics than the one loop calculation that Park et al. Did. To summarize, KFT is an analytical particle-based approach for cosmic large-scale structure formation, and therefore a very good tool to calculate momentum density correlations, as it is particle-based. We will cover the basic properties of the transverse momentum density field, especially on the large scales, and we see that our mean field approach for interactions apparently includes more non-linearities than the one loop approach of Park et al. Did. Thank you for your attention, and I'm glad to answer any questions.